Hey, Golden Eagles. I'm having a little trouble with my PowerPoints. So I'm just going to start from this screen. I did borrow it from the book. I am jazzing it up. And I am also using information from a website from Carleton University where they teach geosciences. We'll get to those pages in a moment. In your Cornell notes, you are going to add these objectives and essential questions. You are students, and you will fit scatter plot data using linear models with and without technology. And you will use linear models to make predictions. The essential question I'd like you to be able to answer when we finish is, how can a scatter plot help me make better decisions? What does it mean to fit the data? Pause the video now if you need to, and copy these questions into the appropriate boxes on your Cornell notes. If you're ever without your Cornell note sheet, I think you can probably remember what they look like. Put the objective and the essential questions at the top of a regular piece of paper, making sure you add your name, class, this is Algebra 2 with Miss Hudson, and the date, whatever day that may be. And then leave room, like a big box at the bottom, for your notes, and use the left column, you know where they have the red line and the dots and the holes are? That will be your questions box. Now that we've copied our objective and essential question, our vocabulary words go in the question bar at the side. Of course, later you'll be writing your own questions, but for right now, I want you to be focusing on the vocabulary. We have regression, correlation, which we did handle earlier, but if you didn't, it comes up again. Line of best fit, a correlation coefficient, and trend. Take a moment to write these down now. So this is a screen print from the carleton.edu website where they talk about geosciences. And I thought it was interesting and relevant. How do I construct a straight line through data points? And it tells us a little bit about why we would do this. Questions that ask you to draw a best fit line or a trend in the data usually don't want you to connect the dots. We've been over that. Instead, the question is asking you to think about how the two sets of data behave in relation to one another. In general, we fit lines to data when we want to use them for predictive purposes or to determine the general trend of the data. We fit lines to data when we want to use it to figure something out. Now, most scientists will use a computer program to plot a best fit line. We're going to use a calculator. We've done it by hand. But constructing it for yourself by hand is a good way to learn how it's done. That's why we have you do it. Because a computer isn't doing it when you do it by hand, you may find that your line is going to be a little bit different from the one you get with the calculator. But that's okay, as long as you come close. So, now that we've gone over why we do it, how do I construct a best fit line? A best fit line is meant to mimic the trend of the data. Trend is the general way it's going. In many cases, the line may not pass through very many of the plotted points. Remember, we're not connecting the dots. It doesn't have to go through every single dot. Instead, the idea is to get a line that has about equal numbers of points on either side, above and below. Most people start by eyeballing the data. Sorry about that, guys. Computer had a mind of its own. Give me a second to get back on track. I thought it was important that you see that. The most people start by eyeballing data. You kind of figure it out as you go. That's not just me saying that. That's what happens out in the real world. And you look at the data and you ask yourself these questions. Does it look like it's in a line? Like they're all generally doing the same thing? Or is it a big blob? If your dots on your graph were little kindergartners, would they be walking in a good line towards the gym? Or would they just be going all run amok all over the school? That's how you decide. Back to Holt. Researchers, such as anthropologists, are often interested in how two measurements are related. The statistical study of the relationship between variables is called, in case you didn't see that vocabulary word sneak right up on you, let me help you. The statistical study of the relationship between variables is called regression. Take a minute to write that now. If there is a strong linear relationship between two variables, a line of best fit or a line that best fits the data can be used to make predictions. If reading isn't your favorite thing and you still have trouble figuring out which part of that is the definition, I'm going to help you out here. Okay. All of it is a good explanation, but the actual definition part would be what follows. Okay. A line of best fit is a line that best fits the data, and it displays the linear relationship. We use it to make predictions. Alrighty? And again, trying to have the same number of points above and below is a good idea. Now everybody can sketch a line on a graph, but actually finding the equation is what I find to be the difficult part, so I'm going to walk you through a little example to show you how we do it. Alrighty? Here we have a sample meteorology application. Albany and Sydney are about the same distance from the equator. The equator is the line that divides the Earth in half. We make a scatter plot with Albany's temperature as independent. And then we want to see if the temperature in Albany decides the temperature in Sydney. That is to say, does the temperature in Sydney depend on what happens in Albany? What do you think it's going to be? Do you think they're connected at all? Does one depend on the other? Let's see. Should thousands of Australians be very angry when people in Albany make it cold so it's too hot in Sydney? Is that how it works? First, we plot the data points. And they sort of pop in. And we notice that the data set is negatively correlated. As the temperature rises in Albany, it falls in Sydney. When those people in Albany turn down the heat, let's see, as they turn up the heat, it gets colder in Sydney. The poor people in Sydney have to buy sweaters. Next, we sketch a line of best fit, and this is the part that's up to you. You try to draw a line that goes exactly in between what would be our blob of data here. Alright, so we're going to divide it in half. Let's see if the book's line matches mine. There we go. The points are about evenly split above and below. Now for the challenging part. We have to identify 2 points that are on that line we just sketched. For this data, they select 35, 64, and 85, 41. So 35, 64 is 30 is about here, and we go up, so they pick that point, this point here, and then they pick, what was it, over here? I think they pick one of these over here. You select 2 points that are very, very, very close to the line, and you're going to find the actual slope between them. Actually, they're not very close. They have to be exactly on. I made a boo-boo. You find 2 points that are exactly on that line you sketched. So we use our good old friend, the slope formula, to find the slope between those 2 points, which would be our y. Oh, hang on, let me get the pen. Our y2 minus our y1 all over our x2 minus our x1. We want to memorize that. That's our friend. That will tell us m forever and ever and ever. So we end up with negative 23 divided by 50. I would keep the fraction because I like fractions, but if you want, you can always convert the slope into a decimal. From here, you're just going to use the point slope form, where you select a point, and it doesn't matter which one of these 2 points you choose. You use the calculated slope, and you substitute for y1, and you substitute for y1 here. Whoops. Highlighter, y1 and x1, and they use this point here. This is their y1 and this is their x1, and you take this slope and it goes in there, and then you just do math. Alright, we want to simplify it so that the y is by itself, so we have to distribute and add the opposite. And this is what we end up with. This is the equation of the line of best fit. We say An equation that models the data is y equals negative 0.46x plus 80.1. It models the data. It shows us what it could look like. The way a fashion model shows you what the clothes could like if you were 7 feet tall and 5 pounds. But it models the data. This is a much better fit than high fashion. More vocabulary. The correlation coefficient is called R. The way we use M for slope, we use R for correlation coefficient. And it is a measure of how well the data set is fit by a model. All right? The correlation coefficient is a value between -1 and 1. It's never going to be 5. It's always going to be -1 or -0.5 or 0 or positive 1/2. Sorry about that, I have my pen set for flick. If R equals 1, the data set forms a straight line with a positive slope. The closer R gets to 1, the more positive and the more highly correlated things are. The better the data gets along and works together as a team. If R is 0, the data set has no correlation. That's the graph that looks like a blob, the big circle. Sorry again, I keep touching the screen. If R equals -1, it makes a straight line with a negative slope. That is to say, the data behaves like a team. When X gets bigger, Y gets smaller. X gets bigger, Y gets smaller. Remember, negative is a direction, not a judgment. Below are some examples. If you're having difficulty making a connection between the words and the graphs, pause now and add the example graphs to your Cornell notes along with your definition of correlation coefficient. When you make a line of best fit, you can also call it a trend line because it shows us the trend in data, especially when we have a graph where your domain is time and your range is something that depends on time. That's where we get that trend word from. That is to say, felt tip pen, I have a graph here and this is years, and we're going to call this miles per gallon that cars get. And as the years have gone by, over time, you've noticed that our cars have become more fuel efficient and they get more miles to the gallon. As when I was a kid, it was like 13 miles to the gallon. Really, that was good. And now I drive a car that gets darn near close to 30 miles to the gallon. All right. As time has increased, the range, miles per gallon, has also increased. The trend is for fuel efficiency to increase. It increases. We're almost done. One thing I want to warn you about is just because two pieces of information have a strong correlation, that does not mean that one causes the other. Just because time increased, time increasing did not make the miles per gallon get more efficient, all right? Just because time went by, that's not what made it happen. What happened is that as the time went by, we performed increased research and invented new things. Time did not decide. Time did not make this variable here, did not make that go up. But they both increased at the same time. Correlation is not causation. In the summer, more people eat ice cream. Ice cream consumption increases, and drownings increase too. Can we say that ice cream causes drownings? No, but we can say that as it gets hotter, more people eat ice cream, and as it gets hotter, more people swim, increasing the likelihood of a drowning. Be cautious of this as you read and learn and grow. Thanks for listening.